This video is going to look at interpreting proton NMR spectra, and after this video you should be able to explain what causes spin-spin coupling, you should be able to describe the n+1 rule, and you should be able to explain in an exam how the spectra can be interpreted. Already you should have learned that the different non-equivalent hydrogen atoms in the molecule have different peaks, that the ratios of the number of equivalent hydrogen atoms are the areas under the peaks, and that the chemical environment of the equivalent hydrogen atoms is the position of the peak, that's its chemical shift, and the number of adjacent hydrogen atoms that are non-equivalent is the peak splitting. So in this video we're going to be focusing on the peak splitting of high resolution spectra. So if you zoom in on low resolution NMR peaks, they're actually split up into particular patterns, and this is created by something called spin-spin coupling or spin-spin splitting. The reason why it happens is because the applied magnetic field, so the applied magnetic field of the hydrogen atoms on the neighbouring carbon atoms are affected. So the spin-spin splitting gives information about the neighbouring hydrogen atoms, and this is really helpful when you come to work out the structure. We're now going to look at how the number of non-equivalent hydrogen atoms, which we call N, creates the peaks. If we take this example here, we can see this carbon has got an oxygen next to it, so it's got no neighbouring peaks. So the number of nearest protons is 0, and therefore we can say that 0 plus 1 gives us a peak of 1. And we call that peak a singlet. And there is only one peak, so there is only one ratio, which is a peak of 1. Let's now consider these two protons here, these protons B. They're equivalent. They have a nearest neighbour, one nearest neighbour on the adjacent carbon atom, so their signal will be split into two. Because there is one nearest neighbour plus one, it's split into two. We give the name, this is called a doublet, and the ratio of the peak heights is the same, 1 to 1. The hydrogen atom labelled A is adjacent to two hydrogen atoms that are in the same chemical environment. The peak that this produces will be split into 3. We call that peak a triplet, and the ratio of the areas are 1 to 2 to 1. Consider the proton D here. Proton D is adjacent to a carbon which has got 3 protons in the same chemical environment. The signal given off by this proton here will be split into 1, 2, 3, n+1 into 4. We call that signal a quartet, and it has a ratio of peak areas of 1 to 3 to 3 to 1. So now you should be able to memorise the n+1 rule. If there is one hydrogen atom on an adjacent carbon, this will split the NMR signal of a particular hydrogen into two peaks of the same height. Generalising this, n hydrogens on an adjacent carbon atom will split a peak into n+1 smaller peaks. Let's now look at a molecule of ethyl ethanoate, a typical ester, and let's predict its spectrum. On a low resolution spectrum, we would expect to see 3 peaks in the ratio of 3 to 2 to 3 because there are 3 non-equivalent hydrogen environments. But how would it split? Let's first of all look at these 3 protons in this methyl group. They have on the carbon next to them no adjacent non-equivalent hydrogen atoms, and therefore their peak would not split because they have no nearest neighbours. The signal that these protons would produce would be a singlet. The hydrogen atoms in this methyl group, however, have got two adjacent non-equivalent hydrogen atoms. They have two nearest neighbours. So their signal is going to be split into n plus 1, which is 3. The signal given off by these protons is split into a triplet, not because there are 3 hydrogens, because there are 2 nearest neighbours. You apply the n plus 1 rule, the signal given off by these will be split into a triplet. Let's now consider these protons here on B. We call this a methylene group. Adjacent to it, there are 3 non-equivalent protons. These 3 non-equivalent protons, it's got 3 nearest neighbours, so the signal will be split into n plus 1, which is 4. The signal given off by these protons here, protons B, will be split into a quartet. Before we can predict the positions of the quartet, the singlet and the triplet, we need to know the chemical shift, and that's where we would need to go to a data sheet. To simplify the procedure, my advice is to draw up a table, a simple table, with 4 columns. In your first column, identify the protons and label them on the molecule. So I've labelled the 3 non-equivalent environments as A, B and C. I've then given the ratio. Now sometimes this is given as something called an integration trace, and you will see this integration trace by the integration symbol here. So integration means the sum of the parts, integrating the parts. So if you integrate the area under the curve, that will give you the ratio of the protons. So let's go back to the data. What we then do is go to our table with the chemical shifts that you are given to the exam. I'm going to show that in a moment. So the chemical shift will come from your table. The 4th column is the splitting pattern, because that tells you the number of nearest neighbours of each of those protons. So let's have a look at the data sheet. First of all, let's look at protons A. Protons in A are heavily shielded because they're next to this methylene group here. If we now go to our data table taken from your Caboodle textbook, you can see that these protons here on the methyl group next to anything but an oxygen atom have a chemical shift of 0.7 to 1.2. Let's now look at the protons in B. The protons in B are on a carbon which is right next to an oxygen. You can see that they have a chemical shift of 3.7 to 4.1. Because they're not just next to an oxygen, they're next to a carbon which is also double bonded to an oxygen, typical of an ester link. So this is very specifically the proton which is next to the oxygen in an ester group. So that's 3.7 to 4.1. Finally, protons on C are specifically next to a carbonyl compound. And we can see on our data sheet here, the proton that is right next to a carbonyl group has a chemical shift of 2.1 to 2.6. So now we've identified the chemical shift and the splitting pattern, which will help us to deduce the structure of the molecule. If you can recognise some common splitting patterns, you're going to halve the time in which it takes to solve some of these NMR problems. This spectrum here contains a triplet and a quartet. They don't necessarily have to be next to each other on the spectrum. But if you have a triplet and a quartet, you have definitely got an ethyl group in your molecule. The presence of two triplets indicates that you've got a CH2, a methylene group, next to a methylene group. A doublet and a quartet, so a doublet and a quartet, tells you that you have got a CH3 next to a carbon hydrogen, and that might have another group on it but only one single proton. A singlet with 3 protons tells you that there is a methyl group with no other hydrogens on the adjacent atom. And that is just a single with a methyl group. So that could potentially be here with 3 protons. A singlet usually indicates a hydrogen on its own, and if it's got a ratio of 1, it must be an H on an O. It could be an H on an OH. One that is not mentioned here that is really common, if you have got a branched molecule and you have a singlet that has got an integration ratio of 9 hydrogens, that tells you without doubt you have got a carbon that has got 3 methyl groups on it. So that's a singlet with 3 methyl groups on it, because even if we have a proton here, its adjacent carbon has only joined to carbon atoms, not 2 hydrogens. So this is really common in branched molecules. Look out for it. So that's a singlet with a height of 9. This example is taken from task 7 in your chem sheets. Normally you have more information than just the splitting pattern on the NMR. For example, in this case, you've been told that the NMR spectrum has the molecule has a molecular formula C9H16O2. It also tells you that it's got a large peak at 1,705 centimeters to the -1 in its infrared spectrum. The chemical information that's been given to you is it doesn't react with sodium hydrogen carbonate or Tollens reagent. Deduce the structure of the compound. Well, first of all, if you go to your data sheets, you will find out that the peak that is due to a sharp peak at 1,705 from your infrared spectrum is due to a carbonyl group. But we also know that that cannot be a carboxylic acid because it doesn't react with sodium hydrogen carbonate, so it's not a carboxylic acid. It also cannot be an aldehyde because this molecule does not react with Tollens reagents. So that gets rid of those, which tells us it could either be an ester or a ketone. The best thing to do to deduce the structure is take down all of the information and put it into a table. In this spectrum, we've been given the integration. So what I'm going to do is to put those numbers in. So peak A, we've got an integration of 1.2. Peak B is an integration of 1.2 as well. Peak C has got an integration of 5.4. And D has got an integration of 1.8. Now these are simply the ratios of the hydrogens, and they're not whole numbers. We know that our molecule has got 16 hydrogen atoms altogether. If we divide these through by the smallest, we get a ratio of 1 to 1 to 1.5 to 3. Now clearly we can't have 1.5 protons. So what we do is multiply them up. So we've got a ratio of 2 to 2 to 9 to 3 protons. So that comes out to 4.5. If we add all of these up, the hydrogens add up to 16. So these are the exact number of hydrogens in each environment. So I'm now going to put those onto the peaks. So this one here has got 9 hydrogens. Let's now look at the splitting patterns. So A has not split at all, so that's a singlet. And therefore it's got no nearest neighbours. If we look at B, it's split into a quartet, so I'm going to write quartet. and therefore that means it has got 3 nearest neighbours. C is not split at all, it's a singlet, so again that has no nearest neighbours. So those 9 protons have got no nearest neighbours. And finally, if we look at D, that has been split into a triplet, and that means that the protons that are given off that single has got 2 nearest neighbours. So let's recall what we've got so far. We know it's got a C double bond O. We know that the molecular formula is C9H16O2. So let's see what you can deduce from this so far. So remember our little hack. If you see a triplet and a quartet, immediately we know we have got a ethyl group in our molecule. So we know so far that we have got a carbonyl group, we know its molecular formula is C9H16, and we know we've got a ethyl group. And the other little trick that I taught you was if you have a singlet with 9 protons in it, that means that you have got a carbon atom with 3 methyl groups attached. All of the protons in these methyl groups are equivalent, and that is next to an atom that has got no other hydrogen atoms on it because it's not splitting. So let's look at there is one really important piece of information that's missing here, and that is the chemical shift, because that will tell us the position of the proposed structure of the group in the molecule. So let's now put in our chemical shifts. So we can only estimate because the quality of the spectrum isn't great. But A has got a chemical shift of round about 3.5. B has got a chemical shift of around 2.5 to about 2.6. It's hard to tell. If we now look at C, that is about 1.2. Roughly, you can see here, is roughly about 1.2. And D, which is the most downfield, is its nuclei the most shielded, has got a chemical shift of about 1. So using all of this data, you've almost answered the exam question because you've told the examiner about the number of nearest neighbours and the splitting pattern. So what we can do from this is build up some information. I'm going to go for the easiest one. The structure of the group at 9 is definitely going to be a singlet, and we know already that it's the 3 methyl groups attached to a carbon. But we want to work out what's on the other side of this carbon. Let's now go to peak A, and we can see at A we know it's a singlet with 2 hydrogens and no nearest neighbours, and it's got a chemical shift of 3.7. When I go to my data sheet, I can see that the chemical shift is due to a proton which is next to a oxygen which is next to a C double bond O. And we already know there are 2 hydrogens here and no nearest hydrogens on the other side. I also know that there are 2 hydrogens in this environment because of the integration trace. Let's now look at peak B. We know that peak B has got 2 hydrogens, and we also know that it's next to 3 nearest neighbours because it's a quartet. Interestingly, when we look at the chemical shift, it has to be hydrogens right next to a C double bond O. So we've got 2 pieces of data. We know it's a proton next to C double bond O, but because it's split, the signal split into 4, we also know that it's got 3 protons next door. So this is where we can get them a lot of information. So we just know that it's next to a carbon with a double bond oxygen. We know that there are 2 of these protons. And we also know that they are right next door to a carbon that's got 3 hydrogens because their signal has been split into 4. That just leaves us to elucidate the structure of D, this triplet here. Well, we have in fact just identified that triplet because it must be next to the quartet. It's got 3 protons. Here are the 3 protons. Let's just highlight them. These are the 3 protons here. Their signal has been split into 3 because it's got 2 nearest neighbours. So that must be this portion of the molecule here. So let's draw that out again. So it's the CH3, which is next to the CH2, and it's got the lowest chemical shift. So if we go to our data sheet here, we can see that CH3s in that environment have got a very low chemical shift. What we're now going to do is we're going to put all of that data together to construct our molecule like a little jigsaw puzzle. This was the peak produced at D with 9 protons. We then had a peak A, which had a singlet because it's got on the carbon next to it there are no hydrogens, just carbon atoms, and then on the other side of it there are no hydrogen atoms, it's just an oxygen atom, so that gave a singlet. Then we have the ester link, and the ester was joined to an ethyl group and then a CH3, which gave rise to the triplet and the quartet. And there is our ester group, and there is the ethyl group. Let's now look at a typical examination question. This came from AQA 2023, paper 2. Already in the previous part of the question, you'd elucidated that there were 7 different carbon environments. You were also told that the infrared spectrum contained a peak, and the group that was responsible for the peak was a carbonyl group. And the other piece of information that you needed to know was the molecular formula of the molecule, which was C7H12O3. And you're asked to explain what can be deduced from the splitting patterns and the chemical shift values, and this was worth 5 marks. Now, this was kind of scaffolded, but if you draw a table, it makes your life a lot easier when it comes to explaining the splitting patterns. So let's draw a table. Having constructed our table, they've given us the chemical shift first. The integration ratio is quite simply the number of hydrogens, because if you add all of these up, it adds to 12. So the integration ratio in this case is exactly the same number of hydrogens. So there's 2 equivalent protons at A, 2 equivalent protons at B, 2 equivalent protons at C, 3 equivalent protons at D, and 3 equivalent protons at E. Let's just put in the chemical shifts quickly. So that's 4.1, 2.6, 2.56, 2.19, 1.26. The splitting pattern is a quartet, so I'm just going to write a Q. So that means the number of nearest neighbours is 3. The splitting pattern there is a triplet, so the number of nearest neighbours is 2. The splitting pattern there is a triplet, so the number of nearest neighbours is 2. The splitting pattern here is a singlet, so there are no nearest neighbours. And the splitting pattern here is a triplet, again, so there are 2 nearest neighbours. Immediately you can see that because there is a triplet and a quartet, so there's a few triplets there, that tells us that there is definitely in your molecule a CH3 joined to a CH2. There is definitely an ethyl group. Also, you can see that there are 2 triplets. That tells you that somewhere else in the molecule there is a CH and methylene group right next to another methylene group. So you've already deduced 2 fragments of the molecule, and then the splitting patterns. There is also a singlet with an integration ratio of 3, so we know that somewhere else in the molecule, because it's a singlet, it's a CH3 not joined to a CH2, so that's a different fragment altogether. So far, what have we deduced? We've got an ethyl group, we've got a CH2 next to a CH2, and then we've got a methyl group all on its own with no nearest protons. Now, when we need to look at the structures and to find out where the three oxygen atoms are, we now need to go to each in turn, and this is where we need to look at our data sheet. The chemical shift of 4.1 tells us that is due to a proton right next to an ester group. So let's fill that in. But what we also know is that there are 2 hydrogens in this identical environment. And even better, the signal has been split into a quartet. So we now know that there are 3 adjacent protons that have split their signal into a quartet. Let's now move on to the peak at B. The peak at B is due to a proton which is right next to a carbonyl group. So this must be on the other side of the molecule. We know there are 2 protons because there are 2 protons, and it's been split into a triplet, so remember that there must be another 2 nearest neighbours. So let's put that on. Let's now look for the peak C. C has got 2 hydrogens in it. It's got a splitting of a triplet, very, very close to the previous one, so I suspect it's these 2 hydrogens here. So let's draw that again and put those 2 hydrogens in. I'm going to highlight them in red because it must be these 2 protons which were next to the previous 2 that were next to a carbon with a double bond oxygen. Let's now go to the peak at D. It's got 3 protons on it. It's a singlet, and that means there must be no nearest protons, and it's got a shift at 2.19. The chemical shifts suggest that it's a proton next to a C double bond O, and there are 3 of them, and there are no nearest neighbours. So we can be quite confident in suggesting that these are 3 hydrogens right next to a C double bond O. Our final peak at E is a triplet which is right next to 2 protons with a low chemical shift. And that suggests it could possibly be these 3 protons here, because the signal has been split into 3 because the nearest number of neighbours is 2. So let's now draw that fragment out. So that's a CH3 next to a CH2, and the low chemical shift is something around 1.2 to 1.4. So that's these 3 protons here. So you've already described the splitting patterns. You've told, for example, at 4.1 here, what you can deduce is that there are 3 nearest neighbours, and from its chemical shift you know that it's 2 protons next to a CH3 because the signal's been split into 4, and also because of the chemical shift it's right next to this ester group here. So again, we can now draw all our fragments together and propose a structure for the molecule. Interestingly, there was only 1 mark for deducing the structure, and 4 of the marks were for predicting these possible parts of the molecule. So let's now identify them in there. So first of all, this fragment here, which was the ester link joined to a ethyl group, is here. Then the 2 CH2s, the 2 triplets, are here. And then finally the group that was the methyl group that had no other hydrogens, no hydrogens next to it, we can see here that would just give a singlet because it's got no protons on that carbon.